some improvement in accuracy, but what I find interesting are these experiments on synthetic data. So we took, there is this standard MNIST data set where you have images of digits and you want to recognize the 0 to 9 kind of classification data set. And we generated domains by rotating the digits by various angles. Okay, so you have like say digits rotated by 30 degrees, 45 degrees, 60 degrees. And but you know, the cross-grad classifier that we have, that does not know about the fact that in this case domain is actually continuous. It's just given this domain as continuous, as discrete label. And you know, what you see here is the G value in some you know, this Disney embedding, two-dimensional Disney projection of the G values. So our original G we had trained for I think 8 or 60, right? And this is projection in two-dimensional space. And we were happy to find that indeed, you know, the continuous representation of domain makes sense, that 45-degree rotation is between 60 and 30. It has been able to discover that. Across fonts. Yeah, this is across fonts. This is not just one font. Okay? And so now, so this is just saying that we are able to extract G meaningfully. But what is the importance of the perturbation? That is what I am most excited about. Like, how are we able to generalize? And in fact, this is what you will observe. So what now in these slides, you see, you know, the 30, 45, and 60. And the red points are the 45-degree rotated examples perturbed by their domain loss. And if you squint enough, you will find that in this region of 60 and 30, there are more red points than blue points. So after perturbations, the points do try to go across to their neighbors more than the original points. So perturbation does help you kind of inch towards, in case 30 or 60 was missing, then it would, you know, maybe compensate for it by, you know, going towards that direction. So this is the end of my first talk. And now the second one I'm going to talk about, this is about calibration. So actually when these guys invited me, I looked at 2 of my most theoretical papers and you see all of it here. Okay. So this is about training calibration measures for neural networks. So this work appeared in ICML 2018. And again, you know, most of the problems I solved are motivated by practical applications. So I was interested in figuring out why is it that modern sequence-to-sequence networks tend to under-predict long sequences. So through a long path, we came to a root cause that modern neural networks are not calibrated. And that led us to proposing a fix for calibration, which I'm going to talk about here. Yes, I will explain what. Yeah, so there's my next slide. So, so here, so basically what I mean is that, you know, so again, we are talking about standard classification models, and classification, these are probabilistic models, and which when it gives you a label, they also attach a probability with that label prediction. Now that we can also think of as confidence. So very often these labels are also called as confidence. So you have a confidence attached with the prediction. And if the model is calibrated, then the confidence that is attached is sort of equivalent to the correctness probability of that prediction. So give an example. Suppose you have a supervised model which makes 1,000 predictions with confidence 99%. And if this model is calibrated, then the 99% confidence directly reflects accuracy. So you would expect 990 of them to be roughly correct. Okay. And another example, suppose if you make 100 predictions with confidence 70%, then you expect roughly 30 of them to be wrong. Okay. Yes. That's what. And if you know, standard, you know, in the old days when people trained logistic regression classifiers or neural networks of old days with cross entropy loss, this thing came as a side effect. It was guaranteed because this is the property of a sound statistical estimation model. But recently it was found, so there was this paper which appeared in ICML 2017, which showed that even though modern neural networks are so awesome in their accuracy, they are very bad in terms of their calibration. So they provide great 0-1 accuracy, but they are overconfident. So overconfidence seems to be running in the, in multiple layers, right? So, so there is, you are overconfident in the confidence course. So in fact, we tried it out ourselves, when we trained a CNN-based text classifier, and that classifier gave us 61% of its predictions with confidence 99%. So therefore, you expect among these 67% predictions, which you got with confidence 99%, no more than 1% error. But when we actually measured the error, it was 8%, okay, among the 60%, right? No, because it has a cross entropy loss. It says that this is the class label. It gives us a probability distribution over the label. We pick the highest probability label, and that has a probability of more than 99%. So essentially, you think of the classifier as imposing a multinomial distribution over the labels, and we are talking about the calibration of that multinomial distribution. So this is actually a very important property in practical deployments of neural networks. I mean, later we have some very interesting follow-up work talking about the relationship between calibration and the accuracy of beam search, etc., which is used for sequence models. But even for the case of scalar classification, you can imagine that calibration is important when you want to fall back to humans, when you are not able to tell the label of an example. So in mission critical applications, in medical diagnosis, for example, if you are not able to identify a location of a tumor, you want to fall back to a human being. So therefore the model has to be calibrated. Yes. So yeah, I mean, such things are not done. If you would do such exercises, you would not have such lack of calibration. Because the standard, yes, yeah. So standard machine learning people kind of assume that, okay, as long as I use a validation data set to stop and I do not overfit, I would not lead to a miscalibrated model. So this was in fact very surprising for the machine learning researchers. So, then now if you think about calibration, now it's very easy to achieve calibration, right? If you only care about calibration, to all my predictions, first I will use a validation data set and figure out what is the accuracy of my classifier. And now with all my prediction, I will give that as the confidence. Then I will of course be calibrated, right? But then it's not very useful, right? Because you want to predict a lot of examples with high confidence so that you don't have to fall back to humans. So let's imagine this application of calibration, that if the probability value of a prediction falls below a threshold, you will use a human to intervene and get a prediction, right? So in such applications, you want to make lots of predictions with high confidence, provided the confidence is warranted, right? So that's not useful. So now what is accepted, in fact, that paper from ICML 2017, it sort of concluded that a fix to lack of calibration is temperature scaling. Because modern neural networks tend to be overconfident, what you only need to do is to dampen the confidence using a learned temperature scale. So you sort of take the probability distribution and make it blunt, okay? And that actually has been shown. If you look at the metrics of calibration error, those will of course improve, okay? But then our claim was that throttles valid legitimate high confidence predictions. So can we plan for better calibration during training? Yes, yeah, it's almost like the first one, you're right. It's just on a continuum, yes. So, so now before we do that, I just want to sort of state some results again from, this is somebody else recent work from actually ICLR 2018, which tries to sort of pontificate on why is it that modern neural networks are miscalibrated. So because the training objective for these neural networks that we were measuring, they all are negative log likelihood, which is a theoretically sound objective. And in fact, in the past, logistic regression classifiers and neural networks trained with cross entropy loss, this is like we are talking about 2005 kind of time frame. They were known to be well calibrated. This was this paper from Rich Caruana and his team, and that sort of once and for all settled this point, at least for practitioners, about which classifier is calibrated and which is not. And then this was revisited 12 years later in this 2017 paper, which suddenly discovered that modern neural networks are not calibrated, even though they are trained with the cross entropy loss. So then this paper in ICLR 2017, it basically claimed that modern neural, so this graph is interesting. It shows that as you proceed with training, and here you have error or negative log likelihood for test data, and it was found, this is on a CFAR 100 image classification task, it was found that forget about this big shift that came about because suddenly you changed the learning rate, but it was found that after a while, even though you continue to reduce on test error, your test likelihood increases. So modern neural networks can overfit on likelihood without overfitting on 0-1 error because they have such large capacity. Okay? So there can be some parts of the network which will be busy improving your 0-1 error, whereas that same action for some other examples could cause the negative log likelihood to overfit. So our solution was to add a calibration loss as a regularizer. So now I'm talking about this work we had in ICML 2018, where we said that a more principal solution is to train a neural network with a calibration regularizer, a regularizer for minimizing calibration error, which we are calling CE. And you have your standard negative log likelihood objective, plus now you have this term which tries to minimize calibration error. So in order to explain our term, I'll just introduce some notation. So you have during training, you have sampled X and their correct label Y star from this distribution T, and you apply your network, your function, neural network, and that gives you a prediction Y hat, and the confidence that it assigns to Y hat, let's call it R. And now, along with this prediction Y hat, given the true Y star, you can assign a correctness measure. In this case, let's assume it's 0, 1, it's either correct or incorrect. So with this as the notation, we can actually just look at what we mean by calibration from a probabilistic perspective. What we want to claim is that if you have a model theta and you are measuring on some distribution T, then in a well-calibrated model, the probability of correct prediction among all predictions made at a confidence level of alpha, that has to be equal to alpha. That is just the definition of calibration now in equation form. Now, I will just rearrange these equations, and it's just easy to see that with a slight rewrite, this same equation can be written as follows, that 1 minus alpha times the probability of the confidence values among the correct examples should be equal to alpha times the probability of the confidence values among the incorrect examples. So here, you think about it, we are trying to match two scaled distributions. The distribution of confidence values of the incorrect examples with the correct examples after scaling them with either alpha or 1 minus alpha. So the moment, for a long time we were struggling how to do it. And the moment I saw this matched form, I said, hey, I have encountered this before. And in machine learning, this has been very nicely solved with kernel embeddings. If you want to match two distributions and you want to do this without actually first estimating the distribution in some parametric form and then trying to match them through some KL distance instead of going through this roundabout way. If you're only given samples from these two distributions, then kernel mean embeddings is a very powerful tool. And in order to apply that, then we did a few more steps. And then we said, okay, so the same thing can also be written equivalently as follows. So we are saying that if you look at examples, summing over all possible values of C, which is 0 and 1, then C minus alpha times probability of C, comma, the confidence value, this should be equal to 0. This is some kind of a balancing constraint. And, through this trick of kernel embedding, so which turns out that it's a very powerful and practical instantiation of an integral probability measure. You can claim that, so we came up with a measure of calibration error, which I'm going to define through these 3 steps. So let's say that you have some RKHS space H, which is induced by a kernel K, and with a corresponding feature mapping, sorry, this has to be mapping phi. Then we define a calibration error, which we call maximum mean calibration error, MMCE, as equal to the norm of the expected value of T minus R scaled by this feature embedding. Okay, so normally when people talk about mean kernel embeddings, they calculate the feature embedding and they just take the mean over the sample. But for our problem of calibration, we scale it by C minus R. Okay, and now if you convert this into a sample estimate over multiple examples in your set test data, then this is the corresponding finite sample estimate. And now if you expand out this RKHS this phi into the kernel form, it turns out to be this very simple measure. It just says that in your test data, you look at pairs of examples and you require that their Ci minus Ri value times Cj minus Rj value scaled by this kernel, which is large for nearby points with nearby confidence, and large, and small otherwise. So if you sort of apply this measure as a regularizer, then you will try to make sure that points which have nearby confidence values follow some kind of a balance between their correctness and confidence values. Okay. Sorry, I know that I've been teaching for many years. I know this part is not coming across, but this actually worked quite well for us. And here are some properties of this measure. We have proved in the paper that if you have if the two distributions, like the distribution of the confidence value of the incorrect and correct examples, if they are Borel probability measures, and if K is a universal kernel, then the measure, that MMCE measure that I just described, it is 0 if and only if the distribution is well calibrated, perfectly calibrated. This means that what we have defined, this MMCE, is the proper scoring rule. And then we also shows that it enjoys decent convergence rate over finite samples. And then in practice also we got much higher reduction in calibration error compared to temperature scaling and other methods. But as I said, it's very easy to reduce calibration error. Okay, what is interesting is whether you can reduce calibration error while keeping around high confidence predictions. Yes. Yes, it can work with any method, but it's just that neural networks tend to be overconfident and miscalibrated. Yeah. So basically, I'll just end. This is my last slide. So here I want to show how by this MMCE method, which we apply at the time of training, we are able to make lot of high confidence predictions while maintaining calibration. So in this pie chart here, what you see, the blue part, it indicates the fraction of examples which are predicted with confidence above a threshold. We have picked a threshold of 0.99. So this was an image classification task, and we found that in this task, CFAR10, 89% of the examples were predicted with confidence above 99%. Okay, and so you expect that among those 89% examples, the accuracy should be 99%, but it was not. It was 97.65. Okay, it's lower. So now, therefore, it is not calibrated. So, so the temperature scaling, if you did temperature scaling on these outputs, then you found that instead of predicting 89% examples, you predict only 40% example with confidence above 99%. And this is the calibrated model because the accuracy there is 99.69. Okay. Now, what we do with this MMCE based regularizer added at the time of training, we find that we are able to make more predictions, like 72% predictions, and the accuracy is also above 99%. So it's both calibrated and it predicts a lot more examples with high confidence. Question? Yes. Yes, yeah. Yeah, I think that's interesting. We didn't do that. Yeah, yeah, we should. That's right. It should not perturb anything. Right. Yeah. Yeah, that's true. We have not done that. Okay.